Good morning. We'll start with section 931. Open your toolkit to page 54. Try the warm-up from lesson 931, on page 54. Pause me when you're done, come back, and then let's check this warm-up. I want to remind you that the exponents beats powers. Powers beats logs. So before we even start anything, let's just review how can we figure out the limit as x is approaching infinite for each one of those expressions. The exponents will take any form of a number to the power of x. So it could be 2 to the power of x. It could be 7 to the power of x. It could be 10 to the power of x. But recall that with the higher base, you can beat 10 to the power of x beats 2 to the power of x. 3 to the power of x beats 2 to the power of x. So this is the exponents. The power will be, you have x to the power of a number. So x to the power of 3, x to the power of 4, x to the power of 5, and again, x to the power of 10 will beat x to the power of 8. And then power beats logs. It could be logs, it could be natural logs, it could be e to the power of a number. So all of these would be in the same category. So exponents beat powers, powers beats logs, and this is the main idea about how the limit will approach is infinite. Now you want to look at the dominant term from the numerator and the denominator. Looking at the first question, the dominant term from the numerator is 2x cubed. It's just one term. And the dominant term from the denominator is 3x to the power of 2. Out of both of them, if I circle both of them, the dominant term, which one would win the race to infinite? It's eventually the one that has a higher exponent. So it's x to the power of 3 will beat x to the power of 2. So this will go to either infinite or negative infinite. But there is no negative attached to this whole term, so it would be just an infinite. For B, I have 7 to the x to the power of 7. So this is a power equation, and this is the bottom is an exponent equation. We know exponents beat powers, so this will go to 0. So if the dominant term is in the denominator, it goes to 0. If the dominant term is in the numerator, then it goes either to infinite or negative infinite. If they have equal powers, again, only equal powers, then it would be the coefficient of the numerator and the denominator. Moving on from this one, let's be careful. The dominant term from the numerator is 6 to the power of x. The dominant term from the denominator is this one here, which is 3 to the power of 2x. Looking carefully, if I want to simplify, it's 6 to the power of x still from the numerator, but the denominator 3 to the power of 2 raised to the x power. On the top, it would be just 6 to the power of x. On the bottom, it would be 9 to the power of x. So what appears in the beginning, it was the dominant term on the top. After simplifying, eventually, your dominant term is in the denominator, so this will go to 0 because the dominant term is in your denominator. Now, the tricky question is coming up next, which is D. The dominant term from the top, from the numerator, is 5x. The dominant term from the denominator, it's log of 2 to the power of x. But remember, I know that powers beats logs, but this is not a log expression. A log expression would be in the form of log of any base of x. But log of maybe 5 to the x, eventually this is not a log expression because it's x times log of 5. So it turns into a power equation. So if I simplify, it will be 5x divided by x times log 2, log base 10 of 2. Now they have equal powers, so the limit as x is approaching infinite, since they have equal powers, it would be the coefficient of your numerator and your denominator, and it would be 5 over log of 2. So again, just be careful. Log of x, yes, this is a log expression, but log base, whatever base you have, now, since there's no base here, it will be 10. But log base 10 of 5 to the power of x, this is not a log expression. It's eventually a power expression because the exponents drop in front of your expression, turning that to a power expression. Moving on, I have this question here. So moving on to E. So if I have to imagine drawing this function, again, I'm trying to do a sketch. if I have to do this kind of function and I'm not doing that correctly, it looks like a wave in general. The sine or cosine will look like a wave with different shift, which is I'm not concerned about the shifts at this point. But the limit as x is approaching infinite, this side, the behavior of your right end of your graph, it's fluctuating between going up and down and up and down. That's why we can say simply it does not exist. The limit as x is approaching infinite, it's not going to a specific point because it's keep going up and down forever. So it does not exist. Last question. In the warm-up, the dominant term from the numerator is 2x. The dominant term from the denominator is square root of 3x squared. Remember, we need to simplify so we have a better picture about what's the limit as x is approaching infinite and what's the dominant term from the top and the bottom. Still 2x, we cannot simplify this one, but on the bottom, if we think about it, it will be square root of x times x. Now they have equal powers, and since they have equal powers, the limit as x is approaching infinite would be the coefficient of your numerator and your denominator. So it would be 2 over square root of 3. Now open your ebook in your notes section 931, and the section is talking about walk this way, and we're going to be talking in this section in general about the velocity and position graphs. There are several ways to understand motion. One way is to plot how far an object is from its starting position at any given point. This is called the position graph. Another way is to consider the rate at which an object is moving as time changes. This is called the velocity graph. We will investigate both types of graphs and explore the relationship between them over the next few lessons. So 931 and 932 definitely will be going over the position and velocity graphs. For the people that are taking physics, this will come very easy for them that took physics in the past or are currently taking physics. This concept will come easy to them because you've took already this concept. We'll start with problem 90, and I just before I even dive into this problem, I just want to show you the differences between the velocity graph and the distance graph and the differences between them and how the lines or the horizontal lines or how the graph will look like. When we're looking at the velocity graph, it would be, so if I'm not going to dive into I'm just going to talk in general. For the velocity graph, it will always appear at horizontal lines. So it will be, you will see horizontal lines. Oops. You will see always horizontal lines. But if this is if I'm imagining that this is walking, then eventually running will be a higher horizontal line. If it's stopping, then there would be no line. It would be kind of like you will see it an empty line on the x-axis. So walking would be, maybe if you chose this is your walking, and we'll go in details when we move into from a velocity graph to a distance graph, and from distance to velocity will be more specific. But in general, if you're just trying to draw a scenario that was given to you, you need to know that running will have a higher velocity, a higher horizontal line compared to walking. And walking slowly maybe will be just right here. So walking slowly would be maybe lower than walking in general. Running will be a higher line compared to your running and compared to your walking, and you're walking slowly. Now, if I'm looking, so this is in general the velocity and how it appears. So the velocity always will appear as horizontal lines. For the distance graph, it will be kind of slanted lines now. So if I imagine that this is going to be my walking, then my running will be a steeper line. So think about it. It would be a steeper line if you're running compared. So this would be your running compared to walking. Again, I'm not doing I'm just trying to talk in general about my walking and running. Now, if I'm looking at stopping, so you're not doing any more, if you're not walking any distance, then it would be looking like a horizontal line. So running would be a line with a slanted line with a slope that's steeper than the walking. You're if you're stopping and there is no motion, it will appear like a horizontal line. So these are the main differences between velocity and distance graph. Again, the velocity will appear like, your horizontal lines. The distance will be appearing as slanted lines, but just be careful with the motion for each one of them. We'll look at this problem. So we have a scenario of walking for 5 seconds, stopping for 5 seconds, repeat the same pattern for a total of 30 seconds. So again, there's just walking and stopping here. So the walking would be the same speed. If you're walking, it should be the same speed. So I'm gonna walk. I'll pick a specific velocity, like, you know, with walking a specific speed. So maybe this is my walking for the first 5 seconds, and then I'm stopping for 5 seconds, so it will be appearing as nothing there. And then from 10 to 15, I'm going to be walking. They said it's the same speed. They didn't mention that we'll be starting to walk faster. And then stopping from 15 to 20, and then walking again from 20 to 25, and then stopping again from 25 to 30. So again, the velocity graph will appear like horizontal lines. Now with the distance graph, I need to pick, like, you know, my speed, like, you know, what would be, like, you know, my slanted line, what would be the speed of my slanted line. So here I'm going to be walking for the 5 seconds and then stopping. So a horizontal line, and then another slanted line with the same speed as this first one. So here is again walking and then stopping and then walking again and then stopping again. Please make sure that you're just like going along with me with the notes. And this will conclude the first one. Moving on to B. You're walking for 10 seconds, stopping for 15 seconds, running towards the finish for the last 5 seconds. So if I have to I have to walk for 10 seconds. So here's my walking. I'm stopping for 15 seconds. So like from 10 to 25 would be stopping. So it's not going to be anything. The last one you're running. So this would be a velocity that's higher than like when you're walking. So I'll pick a different velocity because I'm running. So it will be a higher horizontal line compared to the one that you started from the beginning. The following one, for the distance graph, I have a slanted line, so I'm walking for the first 10 seconds. So I'll pick a speed. Again, when we get into more details, when we're converting from distance to velocity, it will be a different scenario, but we'll be more careful about it and we'll have a better picture about it. So you're walking for the first 10 seconds and then stopping for the following 15 seconds. So up to here, it will be a horizontal line because you're stopping for the distance graph. And then the last 5, so it will be a steeper line for the last 5 seconds. So maybe a steeper line. This is definitely, if you look at this line compared to this line, so this will have a steeper line compared to this one that's here. Third scenario, you're stopping for 10 seconds, you're walking for 10 seconds, and then walking slowly for 10 seconds. So you're stopping for the first 10 seconds. So it's not going to appear anything on my velocity graph. Remember, your velocity will be always horizontal line. The distance will be appearing as a horizontal if you're only stopping, but velocity will be always horizontal lines. You're stopping for 10 seconds. You're walking quickly for 10 seconds. So I'll pick a higher velocity. So from 10 to 20, you're walking fast and then walking slowly for the last 10 seconds. So maybe my graph will be right here. So I'm not appearing anything for the first 10 seconds. I was stopping, walking quickly, and then walking slowly for the last 10 seconds. If I'm trying my distance graph, walking, it will be appearing as a horizontal line for the first 10 seconds. You're walking quickly. So from 10 to 20, it will be a steeper line compared to the 20 to 30. So I'll have a steeper line here maybe. And then so a steeper line here. And then I know that the last 10 seconds, oops, I made a mistake here. So I need just to erase that. So here's my steeper line. And then the last 10 seconds, I'm walking slowly. So maybe this is definitely, so if I compare this line compared to this line here, this is definitely this line, which is like, you know, this one that I put right here is definitely steeper than this line because here you're walking quickly, here you're walking slowly. The last scenario, they're saying they're walking slowly for the first 30 seconds. So for the first 30 seconds, you're walking slowly and you have the same speed. So this will be just appearing as a horizontal line for the first 30 seconds. The second one, you have a slanted line. It will take the same slope all the way for the first 30 seconds. So I can just draw a line for the first 30 seconds. And you're walking slowly from start for 30 seconds. So this is the scenario that you have. The graph to the right is a position graph, and you want to write a scenario that would describe this motion. Looking at this one, I see that you're walking for the first maybe 2 minutes. If I imagine that this is time in minutes, you're stopping and then you're taking a couple quick steps and then stopping back again. So it seems like, I'm walking for 2 minutes, stopping for 2 minutes, and then taking a couple of quick steps for like maybe a second, 2 seconds, and then stopping back again. So if I so this is my scenario that I can write here. But for B, you want to change that position graph into a velocity graph. We'll have more precise information when we get into an example, when we want to change one from a velocity to a distance and one from distance to velocity. But we're going to try to do a sketch on this one. So the first 2 seconds, I'm walking. And then I'm stopping for the following 2 seconds. So it's not going to appear anything horizontal line on the x-axis. The following maybe couple of seconds would be like you're just walking quickly. So it will be a horizontal line that's definitely higher than the first one. And then stopping back again the remaining of the time. So here we go. So here is I changed my velocity graph to a distance, my position graph to my velocity graph. We'll go over question 96. Consider the function f of x is equal to x squared minus 3x plus 1. What happens to the secant line determined by 2 points on the graph of f of x as the points get closer and closer together? So if this is my function, which is right there, and if I have a secant line, this could be a secant line because the secant line will cut this graph into equal 2 points. But if the 2 points are getting closer and closer together and very close, think about it, that secant line will turn into a tangent. So if the 2 points are getting closer and closer together, that secant line will be a tangent line that would touch that graph at 2 exactly. What is the point on the graph when x is equal to 2? So if I look at this, my graph, at 2, the graph will be equal to 3, but we can definitely check that by putting the 2 inside our equation. So 2 times 2 squared minus 3 times the 2 plus the 1. 2 squared is 4. 4 times 2 is 8. 8 minus the 3 times 2, which is 6. So you have a 2. 2 plus the 1 is 3. So what is the point on the graph at x is equal to 2? Then this would be 2, 3. We already sketched the tangent line at this point. So here is the tangent line, which is touching that graph at x is equal to 2. And it would be touching that graph at 1 point. Exactly what 1 point. You want to write an expression for the slope of the line between 2 plus h, comma, f of 2 plus h, and 2, 3. So think about it. You want to find the a rock, and then for e, you're finding the I rock from 2 to 2 plus h. So if I want to do this one, I'll try to do my work outside all of this problem. So I'll start by finding f of 2. And f of 2 is equal, we just found this one by putting that into our equation, which is 2 times the 2 squared minus 3 times the 2 plus the 1. And we found out that that was equal to 3. Now I want to find the f of 2 plus h. I want to get all of my work ready. So I'll do 2 times the 2 plus h squared minus 3 times 2 plus h plus the 1. Now simplifying from there, 2 times the 2 plus h squared would be 4 plus 4h, sorry, plus h squared minus 6 minus 3h plus the 1. Simplifying further, then I'll have 8 plus 8h, I'm trying to do my distribution, plus 2h squared minus 6 minus 3h plus the 1. Let's simplify and see if there's any like terms. So I'll have 2h squared. The 8h and negative 3h will be simplified to 5h. And I have 8 minus 6 is a 2 plus the 1 is a 3. So I'll put here plus 3. Now I'm ready to do my a rock and my I rock to find the slope of the tangent line at x is equal to 2. So now all we're trying to do, we have this line. So think about it. I have this line. And that tangent line, I want to find the slope of that tangent line at x is equal to 2. So I'll start by doing my a rock at this point. And your a rock is equal to f of 2 plus h minus the f of 2 all over 2 plus h minus the 2. F of 2 plus h, I had it completed as 2h squared plus 5h plus 3 minus f of 2, I have it originally as a 3 divided by 2 plus h minus 2 is equal to h. Simplifying further, you have your 3 and negative 3 cancel out, and you have a 2h squared plus 5h all over h. Now, if I pull an h from my numerator as a GCF, it will equal to 2 h out. Oops. H out. It will be 2h plus the 5 divided by h. Now the h's cancel out, leaving us with 2h plus 5. I have found that my AROC is equal to 2h plus 5. Now I can find my IROC, so the instantaneous rate of change, which is the limit, as h is approaching 0 for the function that we get from our AROC. Putting the h inside my equation, that will equal to 5. So your IROC is equal to 5. Recall this 5 means it's the slope of the tangent line at x is equal to 2. So my slope of that line, so if I have that blue line and I want to write the equation of that line, which is what's required in F, write the equation of the line tangent to the curve at x is equal to 2. I already found my slope is equal to 5. Now, I need another point on this graph in order for me to write my equation. The point I have on this graph is 2, 3. So my point is 2, 3. My slope is equal to 5. Now I have everything needed to write my equation. So I'll put y minus the y1 equal to m times x minus x1. My y minus the 3 equal to, your slope is 5. The x minus the x1 from the point, it's equal to 2. So your equation will be y equal to 5 times x minus 2 plus the 3. And here's the equation of the slope of the tangent line at x is equal to 2. So the slope, you find it from your AROC and your IROC. As soon as you find your slope, you can get a point. You have a point on the graph, which is 2, 3. Take those two things and try to write your equation. Have a great day, and I'll see you back when we move on to section 932.